Next, I want to take a look at the components that constitute a robot and then try to analyze the effects of these components on the agility of the robot. And more precisely, we'll be looking at the stopping distance of the robot. So this chart illustrates some of the design choices you might have if you go online. So I've chosen to visit DJI.com and pull off some frames that you can buy off the shelf. DJI is currently the largest manufacturer of drones, and they have a wide selection of frames, batteries, propellers, and motors. In addition to that, you need an autopilot. Pixhawk is one that's open source and sold by 3D Robotics. You can also buy high-level processors, such as those made by Intel. You clearly need the autopilot for doing low-level control, and you need something like the Intel processor you see here to do high-level computations. You want to pay particular attention to the weight of each of these because eventually your robot will have to carry these as it flies. So the control architecture you might think about involves using this low-level processor to drive the motors and the propellers, and a high-level processor like the Intel, which communicates with the low-level processor and commands the low-level processor to drive the vehicle. In addition, you also want to have something that complements the autonomous system, a radio controller, in case you have to take control of the vehicle. So we show standard components here that you can buy off the shelf. This is an example of an outdoor platform that we've built. And in this video, you will essentially see that we have taken standard off-the-shelf components, the DJI platform with motors that you can buy from the DJI website, with a simulated payload. It's a 600-gram payload, an aluminum block that simulates all the payload we might want to carry in the future. It also has on board a 721-gram battery. So this platform has a thrust-to-weight ratio which is greater than 2.7. And this is important. If you maximize the thrust-to-weight ratio, you essentially maximize the acceleration, as we've seen before. In addition to the processors, you also have to carry sensors. Here we show two sets of sensors that we commonly use in our laboratory: a laser scanner, and the laser scanner weighs about 270 grams, a camera system that weighs about 80 grams. And you also want to think about power consumption, and there are two sources of power consumption. First, the device itself consumes power. It's roughly 10 watts for a laser scanner and 1.5 watts for this camera system. But in addition, you're carrying these two payloads. The fact that you're carrying a 270-gram laser scanner means you're burning roughly 50 to 60 watts of power. Likewise, the fact you're carrying an 80-gram camera means you're burning roughly 15 watts of power. So you want to think about how heavy a sensor is. You also want to see its range. And all of those play into how fast the vehicle actually can go. Because longer the range, longer the stopping distance can be. You can detect obstacles far away, and therefore you have more time to come to a stop if you see an obstacle in front of you. This in turn allows you to go at a higher speed. Of course, longer the range, the heavier your sensor might be, and that in turn increases the weight of the platform. Well, if it increases the weight of the platform, it'll decrease your thrust-to-weight ratio. So this is an interesting design space to explore. So here are some examples of platforms we've built and tested in our laboratory in the last year. All these platforms are autonomous. They're different sizes, they carry different sensors, they weigh different amounts, and they consume different amounts of power.